Well, good morning, everybody. This is amazing, but what we are about to do is we are about to wrap up not just the second half of equilibrium, not just the current unit that we are involved in, because what we're about to do is wrap up the entire school year, or at least the lecture and homework portion of it. So, guys, in order to help you connect what we're going to do today with what we've already been doing, you may remember that at the beginning of the unit, we talked about acids and bases and conjugates. And then following that, we talked about reaction rates, and we talked about the things that affect rate, and we brought those ideas to the table. And then at the not at the very end, but last time what we did is we brought those two ideas together, and we talked about this interesting idea of reactions that go forward and backward at the same time. And we said that we've got reactions that can do this and that simultaneously. And we talked about the idea that these are reversible reactions and that these reactions do not go to completion, but instead what they do is they reach this interesting state that we call equilibrium. And so we then got into this conversation about equilibrium, and we came to this point. We talked about the idea that many equilibrium systems are actually acid and base systems, where the acid and the base turn into a conjugate base and a conjugate acid. But these conjugates then react together, and when they do, they form more of the original acid and base. And as we talked about that, we looked at the model that we demonstrated in class last time. And as we did this, we talked about the idea that we have different speeds for the pathways. And we related this back to the idea of activation energy hump. And if the forward reaction has a lower activation energy hump, and if the reverse reaction has a higher activation energy hump, then the forward reaction will have a faster pathway. The reverse reaction will have a slower pathway, and then we related this to the size of the tubes. That then led us to the demonstration that we did yesterday, last time in class, where we started passing these things together forward and back. And as we pass these things forward and back, we talked about some interesting ideas. Now, guys, understand, you not only need to understand these ideas, you need to understand for the test their connections to the demonstration. So let's do this. Remember that we had a graduated cylinder, actually two, and then remember that we had these glass tubes. And as we use these to represent this model, if you remember, the amount of water that was in the tube was analogous with concentration. And again, guys, not directly in your notes, but stuff that you do need to know. So stuff worth writing down. So the amount of water in the graduated cylinder was representative of concentration. And you may remember that as we played with this, we talked about this idea that when we reached equilibrium, the product tube had 70 milliliters of product in it, and the reactant tube, we'll turn this into a fraction, the reactant tube had 30 milliliters of reactant in it. And so we talked about this 70 to 30 ratio, which we'll come back to in a couple minutes. Okay, so with that said, understand that this 70 and 30 actually is not representative of rate. So when we talked about rate, if you remember, we had a large diameter tube and we had that doesn't really look quite smaller. Let's do that again. And we had a smaller diameter tube. And if you remember, as we started to use these tubes to move stuff back and forth, the large diameter tube was the forward pathway, and then the smaller diameter tube was the reverse pathway. And so what we said was that when this thing reaches equilibrium, we had a small concentration of reactants, but that was going through a larger tube, a faster pathway. Then in our reverse reaction, we had a deeper puddle. We had 70 milliliters of product, so we had a larger concentration, but that was moving through a slower pathway. So we had this amount of water moving backwards, we had this amount of water moving forwards, and we found out that those were equal. So a small concentration moving through a faster pathway was equal to a larger concentration moving through a slower pathway, and those two were equal. And this then brings us back to what is actually equal at equilibrium. And the answer is, at equilibrium, the forward and reverse rates are equal. That is represented by the amount of water, that is represented by the amount of water in the tubes. So now, what is true of the concentrations? And guys, I know this is a mess, but let's look at it and then we'll talk about it. So guys, this is what's representative of concentration. That was our 70-30 ratio. So the thing that is representative of concentration is the amount of water in the cylinders, and that is that was unchanging, 70-30. So again, the thought is this: you need to know that at equilibrium the rates are equal. That was the amount of water in the tubes. Then you need to know at equilibrium the concentrations are constant, and that was representative of the amount of water in the cylinders. Okay, so with that as a quick review, then we can remind ourselves that we came to this 70-30, 7-3 ratio, and that is important for us to then move forward and talk about. Now, guys, understand that this 70-30 or 7-3 ratio is a product to reactant ratio. This idea is important. It's always products divided by reactants. So with that as a shared starting point, now let's get into this, because everything that we have done here on the screen, except for this is all qualitative. This is all theoretical stuff. It's ideas. In addition to that, remember that we did some practical stuff, Le Chatelier's principle. That's the homework that we just graded. But now, guys, what we got to do is we got to turn our attention over here and we got to start talking about the math. So let's do that now. This math comes down to what we call KC. Uh-oh. It's not going to let me draw. Just a moment. Come on, little fella. Here we go. This is going to kick me out. And we're going to go back, and now we're going to go here. Okay, so guys, what we're about to talk about are what are called KC expressions. So what is a KC expression? A KC expression is a mathematical ratio of products to reactants when the reaction's at equilibrium. But guys, notice how this goes. It is products to reactants. Products first, reactants second, and that's our 7-3 ratio. So guys, when we write these, this is how we represent them. Products on top, reactants on the bottom. Keep track of that because that's important. But then, guys, we've got sort of a weird deal going on, because you may remember that while the reactants are turning into products, the products are technically turning back into reactants. So really, it's more correct to say this: it is right over left. And then, guys, as you notice in the slides, it's also important for you to remember, and it's actually is it in your notes? Let's take a look. If not, you should write it in. Oh, there's a line. Guys, remember that just like in our pH calculations, pH is the negative log of bracket H3O, hydronium ion concentration. The brackets mean molarity. Okay, so here's what we know. Kc expressions are fractions, they're ratios. Products are in the numerator, reactants are in the denominator, and these represent the ratio of products to reactants at equilibrium. Again, for us in our water tube thing, it was 7-3. But guys, obviously the water tube thing is not a real life scenario. So now what we need to do is let's talk about a real life scenario. So you have this in your notes. This is the reaction between boron trifluoride and water to form, I think, hydrobromate. I'm not exactly sure. Anyway, H3BO3 and HBF4. Notice it's balanced. So what you need to be able to do, and you'll notice this starts in your notes, what you need to be able to do is you need to be able to write Kc expressions. Now, guys, I'm not going to give you the instructions for this. What I am going to do is show you the Kc expression, and you are going to figure, you're going to figure out the rules. So, guys, this is it. Write it down with me. Given this balanced equation, the Kc expression looks like this. In the numerator, you have the H3BO3, and you have the HBF4, but that's cubed. Then the denominator of the fraction looks like this. BF3 to the 4th power and water cubed. So guys, given the Kc value for this expression, figure out the 3 important rules that allow you to turn balanced equations into Kc expressions. And guys, there are 3. We're going to pause the video and let you talk about it. Okay, now that we're back together, let's go ahead and let's talk about what these 3 important rules are. Well, guys, important rule number 1 is actually right here. Products are on the top and reactants are on the bottom. Understand, if you're hurrying, you're going to screw this up because we read from left to right and we read from top to bottom. So you're going to put what's on the left on the top and what's on the right on the bottom, and that's exactly backwards. So it's always products on top, reactants on the bottom. But then, guys, there's 2 other important rules that we need to talk about. First one is this. If we look at the coefficients, and remember that's an understood 1, don't need to write it. Guys, if we look at the coefficients in the balanced equations, where do the coefficients go? And guys, obviously the answer is right there. So what's the rule? Rule number 2 is this. Coefficients become exponents. So when you write these things, the coefficients become exponents. Now, guys, there's one more rule that you need to keep track of, and frankly, this is the most common mistake that I'm going to see on the test. It's actually a mathematical issue. Guys, you'll notice that these are addition signs. This plus this plus that. But guys, you'll notice that if you come down here to the Kc expression, those are not additions. I think that you understand that these are understood multiplications. Dots represent multiply. But guys, rule number 3 is this. Additions from the balanced equations become multiplications in the Kc expressions. Okay, so guys, all we're going to do now to wrap up the day is we are going to look at, maybe not. What if I just keep clicking? Let's see what happens. All right, hold on. Here we go. Get rid of that. Come back here, and we're off to the races. So guys, given this balanced equation, let's write the Kc expression together. And you'll notice in your notes, you have some words and some fill in the blanks that you need to leave. Well, it's there. Let's go down below. So guys, writing the Kc expression for this balanced equation, we understand, first of all, that the products are on top. So that gives us the SO3. And notice that the coefficient 2 becomes the exponent squared. Then down in the denominator, we have the SO2. Notice that that's squared. And then the O2, which is to the first power, it's understood, it's 1. Okay. So guys, this is the first skill that you need to have. You've got to be able to write Kc expressions from balanced equations. So what's left to do? Well guys, the answer is this. Now you've got to be able to solve these. So it says this, if the final concentrations in this reaction at equilibrium, guys remember that's the point where the forward and reverse rates are equal, that's our 70-30. If the final concentrations are SO2, 0.125 molar, O2, 0.11 molar, SO3, 0.2 molar, what is the Kc? Because obviously we can solve for that, and we can do that by plugging in values. So the concentration of SO3 is 0.20 molar, and that's squared. The concentration of SO2 is 0.125 molar, again squared, and then the molarity of O2 is 0.11 molar. Okay, so at this point, guys, you just need to solve it. And so doing all of this math, when things work out well, guys, the answer to 2 significant digits is 23. So I'm going to give you a moment to run your calculator, about 30 seconds. And if you can come up with 23, that's great. If not, we're going to pretend like you came up with 23. And you can figure out your calculator later. So start plugging away at this. All right, so guys, if you have not got 23 by now, it's probably because you and your calculator need to spend more time together. Now, the mistake that you're going to make is you're going to get so fixated on trying to come up with 23 that you're going to miss all the other new material, and then you're really going to be stuck because you're not going to know what we're doing, and you still can't come up with 23. So guys, turn your calculators off and join me up at the screen. So guys, first of all this, when you look at this number 23, I hope by now when you look at a number like 23 as it's represented on the board, that should look weird to you. It should almost look naked. Guys, when we do numbers in science, we need units, right? A lot of you are really good at leaving off units, but guys, numbers need units. So what are the units for Kc? Well, guess what? For all of you that typically leave units off your numbers, you're finally right. Because guys, this is what is called a dimensionless number. It does not have units. But guys, no units and no value are not the same thing. So what does it mean that this number is 23? Well, guys, I think you understand this, that can be rewritten as a fraction, 23 over 1. But guys, remember that this is products divided by reactants. So what that means is at equilibrium, there's 23 times more products than reactants. That is what this sentence means. If your Kc is greater than 1, remember the alligator eats the bigger number. If Kc is greater than 1, this means you have more product than reactant. Now, what if the opposite is true? What if your Kc is smaller than 1? Understand though, guys, this does not mean negative. When we say smaller than 1, we mean something like a decimal like 0.25. So not negative. Guys, understand Kc can't be negative because molarities can't be negative. chew on that for a minute. But guys, what does it mean if you have a Kc of 0.25? Well, let's rewrite that as a fraction. 0.25 is the same as a fourth. So what does that mean? Well, remembering that this is products divided by reactants, that means that we're going to have 4 times more reactant than product at equilibrium. That is what this means. If Kc is less than 1, not negative, it means you've got more reactant than product. All right, so guys, we are going to do one more of these, and then you are going to have the rest of the day to work on your homework. See if we can get this to go. No, not gonna go. So we're gonna come over here. We're gonna click on this. That's gonna fall apart. We're gonna come back. Okay, so guys, now we're back here. Very simple decomposition reaction. HI breaking into diatomic hydrogen and diatomic iodide. Now again, guys, you've got some information, but before we deal with the information, let's write the Kc value. This time it's up to you. Without any guidance from me, write the Kc value given this relatively simple reaction. Guys, please remember it's brackets and not parentheses. That matters. Brackets mean concentration. Parentheses don't mean anything. All right, so assuming that you're done now, let's look at the numerator. The numerator of this fraction is the hydrogen, H2, and the iodide, I2. But you'll notice there are no exponents because there are no coefficients in front of the H2 and the I2. Then in the denominator, we have HI, the reactant, but that's squared. So guys, now that you've had the opportunity to sort of make these connections and see where your mistakes might be, let's come back to the information given in the problem. And this is a little different. Here's what it says. The Kc for this reaction is 0.39. Now guys, pause and think about what that means. If the Kc is 0.39, is that bigger than 1 or smaller than 1? Well, it's smaller than 1. So let's think about what that means. Remember, our Kc's are products divided by reactants. And if we have a Kc smaller than 1, which one's bigger? The products or the reactants? Well, guys, to have a number smaller than 1, we've got to be dividing by a bigger value. That means at equilibrium, we're going to have more reactant than product. All right, so with that said, let's keep playing with this. So guys, moving along then, let's plug in our numbers. So Kc is 0.39. And then guys, you'll notice that we've got the concentration of H2 and the concentration of I2. Those are 0.2 and 0.18. Now, our denominator is the concentration of HI. But you'll notice the last part of the sentence says, what is the concentration of HI? That's our X. So guys, this is where your algebra skills need to kick in. What does this mean? What does it, well, not what does it mean, how do we solve it? So guys, in order to solve this, the first thing we're going to do is multiply both sides by x squared. On the right, the x squareds cancel. On the left, you get 0.39x squared. Then, as we try to simplify what's going on the right, we're going to take the 0.20, multiply that by 0.18, and that results in 0.036. Now, guys, notice we dropped the units. You don't need to track units through your calculations. You just need them at the end. So, guys, we've got 0.036. Now, how do we get closer to solving this for x? Well, we're going to divide both sides by 0.39. So divide the left by 0.39 and it cancels. Divide the right by 0.39 and we end up with 0.092. Then our final step is to take the square root of both sides. And when we take the square root of 0.092, we end up with 0.03. Now, guys, notice this has a molarity because we're not solving for Kc. We are solving for the concentration of HI. That's a molarity, so this does have units. So guys, that's it. That's what we're doing today. You will now have time to complete homework assignment number 4. Notice, guys, that as you look at homework assignment number 4, in the first 4, well, part 1, A, B, C, and D, you're just writing Kc expressions. And then in 2 through 6, you are solving for the thing that you're not given. Guys, notice in numbers 2 and 3, and 4 and 6, you're given balanced equations. Notice in number 5, you're not. But number 5 actually references number 2, and you're given the balanced equation there. So guys, as always, the rest of the time is yours, which is a lot of time. The rest of the time is yours to work purposefully and productively in getting this homework assignment done. Certainly, you're welcome to work with the person that's there with you. And guys, please, if you need help, invite me into the conversation. And you really ought to get this done before you leave today. So guys, let me know how I can participate, and let's get to work.